Sharing my screen. So GNG 200. Today is March 10th, the last day before last lecture before the break, and today we will finalize descriptive statistics, and we'll start the inferential statistics. Mainly the point estimation or parameter estimation. I put a few announcements also yesterday about the computer assignment 2 and midterms. So we'll have the makeup. It will be on Wednesday, 12:30. And for those who missed the first midterm, so all the information are on Blackboard, and you should have received it by email as well. So let's try to pick it up from where we were talking about last time. We did the numerical measures. So last time we did numerical ways to present the data, and we started doing the graphical representation. And we said the first way that we talked about was the stem and leaf diagram. And the best way to do the stem and leaf diagram is to, again, to do an example. So assume that, oh no, not this one. Assume that I have this set of data. We have this set of data where you did a kind of experiment and you want to present the data for your boss, and you decided to use stem and leaf diagram. And stem and leaf diagram is just you split your numbers, you split your data into two parts, part that you call a stem and part that you call a leaf. And in this case, the way we'll split the numbers is the singular digit is the leaf, and then the 10th and 100th digits will be the stem. So we'll do it for all numbers. So this is the stem, this is the leaf, and we'll put it in a way that will look like this. So our diagram will look like this. Sorry. So let's take this shape, and this is what we I have a class now. So this is the way we will present it. So as you can see, the way to read this table is that here the data, which was 76, is split into 7 as its stem and 6 as its leaf. 87, 8 is the stem, 7 is the leaf, and so on, all the way. So you put your data in a better format like this. And why is this better? compared to the table. Why is this more informative than the table? Again, just looking at the table, you don't get anything about the data. However, if you look at the stem and leaf diagram, you can easily say that the minimum is 76, the maximum is 245, and probably the average is 155, 154, and so on. The data more or less look like a normally distributed data. So you have very small numbers that are small, very small numbers that are very large, and most of the data are in the middle. So stem and leaf diagram is a way to visualize the data in a very nice way, much better than leaving the data as is in terms of table. And related to this, or another way of presenting the data is what we call the, probably one let me say one more thing about stem and leaf diagram. Stem and leaf diagram, how do we pick the stems? So for example, what if, before we go to the next one, what if our all data are, for example, between whatever 80 and 89. So this can be happened. Your data are not very well spread, or you have, or even like you have not, and this is very extreme example, maybe what if, let me take what if our all data is between 61 and whatever 95. So an example can be something like this. Assume that you present your data like 6, 7, 8, 9, and then your data is 1, 3, 4, 5, 5, 6, 0, 1, 1, 3, 5, 7, 8, 8, 9, 1, 3, 3, 4, 1, 3, 4, 4, 7, 8, 8, and 2, 3, 5. So if your data is not, when you split it into the like the singular digits and the 10th digit will give you something crowded like this, you can split each stem, each stem into 2, so that you can have something like this. You can have what we call 6 lower and 6 upper, and then 7 lower and 7 upper, and then 8 lower and 8 upper, and 9 lower.
Upper and lower, you mean more than 5 and less than 5?
Yes, yes.
So that is in the second, right? In the upper, right?
Yes, I will see now. So I will have 1, 3, 4 here, and then 5, 5, 6. So I'll have 1, 2, 3, 4 in the lower, 5, 6, 7, 8, 9 in the upper. The same for the lower, 7, 0, 1, 1, 3 here, and then 5, 7, 8, 8, 9 here, and then for the 8 lower, 1, 3, 4, 4, and then 7, 8, 8, and then 2, 3, and 5. Some people, they go even to more extremes. You can go to more extreme division of the stem, because as I said, sometimes the data set does not help you to have very well distributed stems. So you can split each stem, you can split each stem into, like 6 for example, it will be split into 6Z, 6T, 6F, 6S, and 6E. What's those? What does this mean? So Z for 0, T for 2, F for 4, S for 6, and E for 8. So that, in this case, let me just, I know it looks small, but just to, so the 6 now, you'll have 6Z, 6T, I can manage, a second. So, now following up with the same example, I will take the data for the 6, and I will split it into 6Z, 6T, 6F, 6S, and 6E. And this is applicable, of course, if you have a lot of data between 60 and 70. So 6Z means that you have 0 and 1 here. So you have 1. 6T, 2, you have 2 and 3 here. So there's a 3. 6F, you have 4 and 5. So I have 3 and 4. So F4, 4 and 5. So I have 4. And I have 5. I have 5 and 5. 6S means 6 and 7. You have 7. Here you don't have. For 6E, you do not have anything. So with the 0, you have 0 and 1, 2 and 3, 4 and 5, 6 and 7, 8 and 9. You put it under this category. And so on. So this is, again, this is the stem and leaf diagram, which is, as I said, it's not really well used in engineering. What's more used is the next one, which is the frequency distribution.
Histogram.
Frequency distribution and histogram, which they are related to each other. So how do we do? Because frequency distribution and histogram is just the plot of the frequency table or frequency distribution. So how do we construct the frequency distribution or frequency table? So to construct the frequency distribution, so more or less like what we did with the stem and leaf, we need to split our data into bins, what we call bins now, instead of stems. And instead of listing the data itself, I will just list the number of the data that I have in that category. So we must divide the range of data into intervals usually called bins. And in each bin, we put the number or relative frequency of the data inside that bin. I will do an example this to be more practical. And usually we split the data into 5 to 20 bins. So for the example, for the above example, the frequency table will look like something like this. Let me, instead of spending some time to plot it, let me, okay. So we'll have something like this. Oh, this is hard to keep. Okay. So these are the classes or the bins. Sorry. So I have between 70 and 90, then 90 to 110, 110 and 130. So my bins width is bins equals 20. And of course, yani, you have to be smart in selecting the starting and ending range. So we know from the example that the smallest data we have is 76. So it's not good to start your bin at 76. You start at 70 and end. The maximum was 245, so you end at 250. So now in the first bin you have two data points between 70 and 90, between 90 and 110 you have 3, and so on. So you list the number of, this is how many data points you have or how frequently data is located in that bin. You can also calculate the relative frequency. How do you calculate the relative frequency? Relative frequency is 2 over, for example, 2 over the total number of data. I think here we have 80 data points. Let me check. I think we have 80 data points. Let me go back to the example in my notes. 2, 4, 6, 8, 2, 4, 6, 8, 10. Yes, 80 data points. Then relative frequency equals number inside pin over 80. So this one, for example, this one is just 2 over 80. This one is, no, the same. This is 2 over 80. This is, for example, 22 over 80, and so on. So you can calculate the relative frequency. You also can calculate the cumulative frequency. Cumulative frequency is like the capital F of X that we talked about earlier, where every time you go, you add frequency until you reach all the data, or you reach total frequency of 1. So now, having this table, no, what's this? I hope I did not run out of. Oh, my pencil needs a minute to charge. Maybe we'll do the absence. So let's do the absence, Shabab. Please log into your Blackboard. Let me go to L02 until it charges. Sorry for this. Attendance. So go to Blackboard and Okay, start checking in. I started the clock. Let's do attendance. I know we have only 24 students. Usually students, they start showing up a bit later, but today and they are unlucky. We are taking the attendance earlier. So let's take a minute to do the attendance. Okay, I think it should be charged now. So to plot or to generate a histogram, we just plot the data from the frequency table. So how would it would look like? It would look like something like this. So if we plot the data that, as you can see here, these are the bins, the ranges that we decided on here, and the height of each box is the number of data that we have. So here I have two data points between 70 and 90, so I plot a box of height 2. Between 90 and 110 I have 3. Then I plot a box of height 3, and so on. Between 110 and 130 I have 6, and so on. So as you can see, the histogram will give you, you can plot it, of course, against the absolute frequency or the relative frequency, which is more common, because relative frequency, it will be very close to the probability distributions that we mentioned before, the BDF. So the histogram, usually histogram is an approximation of f of x. And in research, we usually do some analytical work. We derive equations for small f of x, and the way to verify it is we run simulations and we plot the histogram, and we see that there is a good agreement between what we draw and what we calculate. And this is actually what you are doing in computer assignment 2. And I will show you some examples. I promised to talk about computer assignment 2, so I will show some examples a bit later. So we can also, so histogram, again, histogram, using relative frequency is mapped to small f of x. And if you plot plotting using cumulative frequency, this will give you capital f of x, and you should get something like this. So this is the plot if you plot your data using the cumulative frequency. All these figures are from your book. And this is, if you remember, cumulative frequency f of x. Again, you can, this is total cumulative frequency. You can do it as divide by, so this will be 0, this will be 0.1, all the way to 1. So this is 0.8, 0.7, and so on. So this will be your capital f of x. So this is more or less what I wanted to mention about the histogram. And the last graphical way that we want to talk about is the box plot. Box plot is a nice way also to present the data. Is widely used in business, in engineering to some extent, maybe in other fields other than electrical engineering. But box plot is more popular. You sometimes, if you read magazines and like business newspapers, you will often see a box plot. Plot is a way to show a center, spread, shape, and outliers of the data. How does the box plot looks like? Let's how does it look like? It will look like something like this. So let's take it instead of a box plot will look something like this. So what do we need to calculate the box plot, or to draw the box plot? To draw the box plot, we need rank the data from smallest to largest. We need to calculate the first Q1, Q2, and Q3. What are those? These are what we call quartiles. What's quartiles? Q2 is just the median, or the middle point. Q1 is the first quartile. What's the first quartile? Is the data point that splits the first 25% of the data. So if you rank your data from smallest to largest, if you cut it into 4, if this is your data, x1, x2, x3, all the way to xn ranked. If this is your ranked data, then the middle point is Q2, which is the median. Then Q1, if you split your data into 4 parts, this will be your Q1, this will be your Q3, and the middle one is your Q2. Okay, so you need to calculate those. You need Q1, Q2, and Q3, and also you need what we call to calculate IQR, which is inter-quartile range. IQR is just Q3 minus Q1. So you do this processing of the data, and of course, as you know, all of this can be done in a very, very simple computer program. So you have Q1, Q2, and Q3, and Q3 minus Q1. Once you have all of this, this is what you will draw. You will draw. So this is your x-axis. You have the data on the x-axis. This is data axis. So you plot a box. Box starts at Q1 and ends at Q3, and you put in the middle point Q2. Of course, these are not equally spaced, right? Need not to be equally spaced because your data might not be uniformly distributed. You do not have data every that are well separated. So first you draw your box, and then you calculate those ranges. So you calculate, of course, Q3 minus Q1 is the distance between Q3 and Q1. Then you draw what we call a whisker. A whisker, you draw it from both sides. It's a line that go from the Q1 all the way to the smallest data point that is within 1.5 interquartile range. So this point is whatever points you have in your interquartile range. Let's do them probably some numbers. So in the above example, let's do an exact. So in the above example, data, we had data from 76 all the way to 245, right? So if you calculate it, you'll find out that median Q2, which is the median, will be 161.5. The median here, we have even number of data points. So you take when you rank your data, you will take data point number 39 and 40, and you average them. So Q3 will be 161. Q1, which is the data point that separates the first quarter of the data, you'll find out that it is 143.5, and the Q3 is just 181. Again, how did we get those data? Those data are just, if you go back to our example, from this table, you have 1, 2, 3, 5, 8, 11, 17, 25, whatever, 35, 37, 38, 39, 40. So you have 167 and these are not ranked. Sorry, these are not ranked well. From smallest to largest. So you need to rank your data from smallest to largest to calculate Q2. Q2 is the middle point. So you need to rank the data to calculate it, and the same for Q3 and Q1. So once you calculated those, what's IQR? IQR is Q3 minus Q1, which is 181 minus 143.5, which is let me. So this is just 44, 50, 31, 31.5, right? So this is your interquartile range. So when you want to plot the box plot for this example, you will plot a box above the x-axis. This is your x-axis. So the starting will be at 143.5 and the end is 181, and your Q2 is 161, so it's something like this, 161.5. So, and we said we will plot lines that go to within 1.5 times IQR. What's 1.5 times IQR? It's 1.5 times 31.5, which is, let's calculate, 1.5 times 31.5. So this is 47.25. So where's your two sides of the IQR? It will be 181 plus 47.25, which is 228, and 143 minus 47, so 143.5 minus 47.25, so around 96 or so.
Doctors, any numbers more than 228 and less than 96 are considered outliers?
Yes, I'll come to that point. Yes. So this, unless I made a mistake, 1 second. So it's
Sir.
Yes.
Isn't Q2 160.5?
What's that?
The Q2 is 160.5, right?
Q2 is 161.5 according to my notes. But I'm trying to, is the IQR is correct? What I calculated, 181 minus 143.
Just check the Q2. Professor, how you calculate the Q2?
Oh, this is wrong. This is 37.5. The IQR is wrong. It's 37.5. Sorry. So those two numbers are wrong. So this is wrong and this is wrong. So IQR is 1.5 times 37.5. So this is, sorry for this. So I have 1.5 times 37.5, which is 56.25. So now those 2 points will be, if you calculate them right, this will be 237.25, and this will be 87.25. Okay, how did we get this? This is 181 plus 56.25, and this is 143.5, which is this one, minus 56.25. Okay. So now we need to see what's the largest point that is less than 237.25. Largest point less than 237. Let's go to the 230. It's 237, right? So you plot a line, sorry, that go from the box all the way to 0.237. And on the other side, we need to plot a line from the other side that go to the point just above 87.25. What's the point just above 87.25? We have 87. 87 is less than 87.25, right? So the next one is 97. So plot a line just to 97. So those are, we call this whisker. So again, the whisker is just a line that extends from the box all the way to the largest point in the IQR, 1.5 IQR. And this is also 1.5 IQR. So you have to establish those ranges, and then you plot the whisker all the way to the point that is in that range. And then what you do, any point outside those ranges, we consider them as outliers. So here we have one point, we plot it as just a point. So I have 2, 4, 5 here, and I have two outliers from the other side, which is one very close to the range, which is 87, just 0.25 below, and then we have the 76 points. So we call these are outliers. Outliers mean they are extreme points. They are points beyond 1.5 interquartile range from both sides of the box plot. So this is what we have done. We plot the outliers from both sides, and if you have something that is way outside 3 IQR, we call it extreme outlier. We do not have in this example an extreme outlier, but if you have something, a data point that's way like a point, yani most probably it's either you manage to get a rare event in your data, and this happens only to have an extreme outlier. It happens only if you run, if you are collecting very large number of data. So for example, what's this 181? Okay, yeah, someone was correcting me, I did not notice. Okay, so to capture very extreme outliers is, and sometimes in our simulations we have to run 100,000 runs to get very small numbers. Even if in your computer assignment, you can see if you are running generating random numbers from a Gaussian distribution that has a 0 mean and a variance of 1, what's the chances to get a number that is 1,000 or 500? This is very, 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 very rare. Maybe you need to run millions and millions you write a code to generate millions of Gaussian random variables for you to get such a large number. So this is the box plot. I'm not sure. Let's. I think we have what we call a time series, the last one maybe, and it's very straightforward. Time series. Time series is just a graph that plots evolution of data with time. Like in the stock market, like stock prices, for example. You can do it in one day. This is always time in the time series. This can be one day and or 1 week or even years. Those who are specializing in stock markets, they need to this is useful in studying trends and cycles. So I know people who know when to buy stocks and when to sell stocks, because they monitor over the years. They find, for example, in November, December, prices are starting to go up because it's approaching the dividend distribution or the profits distribution of different stocks. So they sell and then they buy around March or April once the prices go down again. So you plot time series just to shows you the evolution of any process or any piece of information that you want to study it against time. There is one topic that I'm not going to cover, which is, and it might be useful for you, for those of you probably in industrial engineering, or we do not have industrial engineering for males, but what we call probability plots. Probability plots is just I need to have an idea about it, is a plot to confirm the distribution that a plot to confirm the distribution that a data fits it or not. So if I give you a piece or a table of data and I can ask you, can you check if this data follows a normal distribution or not? There are, of course, you can plot a histogram and look at the shape. That will give you an idea about whether the data is normal distributed or not. But if you want to quantify exactly if the data is normal distributed or not, we use usually a probability plot. This is something that I will not get into now. Right. So with this, we finished the part of the course on descriptive statistics, and the remaining part of today's lecture, I will do two things. The first one is computer assignment 2. I will just show you what you need to do. So let me stop sharing from. I want to share from my desktop. I want to share which one? It's 1 second. So I will show you. I managed to get all the submissions that I have from previous years, and I will show you two examples. One done on MATLAB and one, I think, done on Python. So it's up to you again, the language that you want to use. So, okay, let me share. This is Microsoft Word, yes. I assume you can see my screen now. You see my screen, right?
Yes, we are seeing it.
Okay, so as you can see, this is the example that you have in your computer assignment. I ask you to generate 500 random variables from a normal distribution with those means and variances. So this student decided to use MATLAB. In MATLAB, it's very simple. You just generate the random distribution rand_n. Rand_n is for the normal distribution of 501 because you want to create a vector, not a matrix. And then just histogram of x and normalization, and the x-axis label is normalization and the y-axis is BDF, and this is the range that he's using. And then he's writing down the equation for the normal distribution so that you plot it on top of histogram to check that what you did is right or wrong, and this is what you will get. As you can see, this is your histogram, and the red one is the curve that, as you can see, the red one is the curve, and the histogram is what is plotted here. And as you can see, this student could have done something more interesting by shifting it because as you can see, the curve is, the top of the curve should be in the middle of the box in the middle. So if you choose your bins, you shift your bins by 1/2, you would have got a better figure. So this is the program that you will need to plot. Very simple, as you can see. And this is just, I'm here showing the example using MATLAB, which I assume most of you either you learned it this semester or you already know it. Very simple way of doing it. And if you know how to do it for Gaussian, you can do it for binomial, you can do it for exponential. You just need to find in MATLAB what's the syntax, what do you need to use instead of rand_n. And of course here you multiply by the standard deviation, and if you want to change the mean, you just shift how do you shift it? You just add whatever. If I ask for mean of 10, you just add 10. If I asked a variance of 1, you multiply by 1. Variance of 10, you multiply by square root of 10. And that's it. You just generate your figure. Poisson, this is Poisson, and so on. So this is one way of doing it using MATLAB. This guy, another student who decided to do it using Python or Excel. I'm not sure. Is this Python or Excel? I use Java programming environment to generate the required random variable and copy the values to Excel to generate the histogram. So it's up to you how to generate it. This is using Java, apparently. You do the Gaussian, and then he put it in Excel, and this is the histogram from Excel. So it's not rocket science. It's for sure it's doable. Use any programming language that you want to use. Excel, I'm sure in Excel you can do it. I did it before. There's a statistical toolbox. You just need to download it in Excel if you have Excel. And then in that, you can generate any random variable. You can do a lot of statistical, even the things that you are going to do in the next few chapters, you will be able to do it on Excel. Okay, so these are two examples that I wanted to mention. Let me go back to my screen here. Where is my screen? Okay, example shown. طيب now we have around 15 minutes. 15 minutes. I think I will not start because the point estimation is an important topic, and I know this is the last lecture before the break. Let me just take a couple of minutes to remind you of where we are in the course, and probably we'll start the topic in the lecture after the spring break. So we said we are doing statistics, and we said descriptive and inferential. So we did this, and in inferential we said it's two main categories. It's estimation, let's say, and hypothesis testing. And in estimation, we'll do point estimation and interval estimation. And hypothesis testing, we just use test on the mean and test on the variance of a random population. So the next lecture, the lecture after the break, we'll start talking about point estimation, where we learn about the when you collect your samples, why are the samples random? What distribution of the samples that you are collecting from a population, and what will be the best way to estimate certain parameters of the distribution. In the past we used to teach two methods. Method of moments, what we call method of moments, and maximum likelihood method. Now I think we will not do maximum likelihood. We'll just do the method of moments for point estimation, and then we generalize that to interval estimation in a very simple way before moving to hypothesis testing. طيب, I will stop at this point. I will give you a light lecture before the break, and I wish you a relaxing break. I hope for those who will continue the course with me, especially those who did not score well in the midterm, take some days off for sure. Of the break. This is a break for you to relax. So I will take some days off, but I will not take the whole week off. Please take 2-3 days off, and then try to catch up with the things that you did not do well in the first part of the semester, and then inshallah you'll have more time to relax later in the summer, inshallah. So I'll stop at this point. If you have any questions, or if some of you are on campus, you want to come and check your exam papers, please, you can come now, or I will be in for like another 45 minutes or so. Or tomorrow I will be in office starting, I'm not sure, maybe at 11 to 1 or 12:30. I will also be around, or after 2, also 2 to 4. I can be in office too if you want to check your exam papers. Okay, so I wish you a good